Example 4.1.4, repeat the previous example using the technique of reflected impedance. So the givens in this problem are the same as in 1.4. We've got a 1.3. We've got a 2500 angle 0 degrees voltage source, AC voltage source, RMS. We've got a impedance here of 0.25 plus J2. We've got a 10 to 1. Man, that's a terrible transformer. Let me try that one again. A little better. 10 to 1 ideal transformer. And then we've got a load impedance here of 1 plus J5. 1 plus J 0.5, not 5. 10 to 1. And again, this is the input of the transformer, VP. This is the output of the transformer, VS there. So I think that covers it. 1 plus J 0.5, 0.25 plus J2, 10 to 1 transformer, 20. Yep, we got it. Okay, so those are our givens. We're again asked to find VP, IP, VS, and IS. And I guess technically we should verify that the voltages and currents multiply together to be the same, i.e. that the power is conserved to the transformer. We demonstrated that in the last example, so I won't do it again. Because really all we're doing is demonstrating a different technique called reflected impedance. And what the technique of reflected impedance is that we can take anything on the secondary side and move it to the primary side just by multiplying by the appropriate turns ratio. For voltages and currents, we multiply by NP over NS, and for impedances, we multiply by the square of the turns ratio here. So we can go the other direction too. It's not commonly used, but you can move things from the primary side to the secondary side, again by the turns ratio. And this example will demonstrate how to do that. So to solve this problem using reflected impedance, what we need to do is we need to move these quantities over to the primary side through the transformer. And so how that looks in an equivalent model is it gets rid of this ideal transformer completely, and the circuit will just look like this. We've got a 0.25 ohms, a J2 ohms, and then we've got two new, the second one should be an inductor, not a resistor. We've got two new devices here, and this is called a referred impedance in this case, and we'll just label that R prime and L prime, indicating that it is been referred through the transformer. That's what that prime is going to indicate in the case of the impedances. So this is still 2500 though. Everything gets referred through the transformer. So this is IP here, the primary side current. The voltage across here is the turns ratio NP over NS times VS, which you'll recognize as equal to VP. So that holds because in an ideal transformer, that's the relationship between the primary voltage and the secondary voltage. VP over VS is NP over NS. So all those same relationships still hold. So that's the circuit model we need to solve for. The only thing that we're missing is what R prime and L prime are, the referred quantities. And impedances are referred using the square of the turns ratio. So this is going to be equal to 10 to 1 squared times 1 plus J 0.5. And so that's equal to 100 plus J 50 is is our reflected impedance from the secondary to the primary here. So those two values, R prime equals 100, not J prime, L prime is equal to J50. Those are both in ohms. So now we can just apply whatever standard circuit analysis techniques we want to this circuit and solve for the quantities that we're interested in. So, KVL makes sense in this case. We would say 2500 angle 0 equals the primary current times 0.25 plus J2 plus 100 plus J50, right? And then if we solve that, we get that the primary current is equal to 22.14 at an angle of negative 27.42 degrees volts right there. So that gives us the primary side current. We can easily get the secondary current just by multiplying that by the turns ratio. Times IP. And so that's going to be equal to 221.4 angle negative 27.42 degrees volts. So we've got those. We can determine the primary voltage just by multiplying IP times RL prime L prime. You could go back and solve the primary voltage as 2500 minus IP times 0.25 J2. Whatever you want to do to determine what VP is. There's a couple different methods. Any standard circuit analysis technique will work there. I'm just going to say that we can solve for the voltage that the primary voltage is just the voltage dropped across R prime, L prime in this case. So VP is equal to IP times R prime plus J XL prime. For some reason the eraser's not wanting to work. There we go. So we've got that right there. So that's going to be equal to 22.14 at an angle of negative 27.42 degrees times 100 plus J50. That gives me a primary side voltage of 2,475.33 at an angle of negative 0.86. Negative 0.86 degrees volts. And then I can determine VS. Since this is a step down type transformer, VS is just a tenth of that. VS is 247.53 at an angle of negative 0.86 degrees volts. So now we've got IP and IS here, and VP and VS here. So this technique of referring the quantities on the secondary side to the primary through the turns ratio of the transformer is very commonly used. It's the most common method of circuit analysis using transformers. And you can see there's just really two things you have to remember. You have to remember that VP over VS is equal to NP over NS. So the turns ratio gives you the primary, and then that is equal to IS over IP. So that's one rule that you have to remember. And so you can refer the primary side to the secondary side just using the turns ratio. And then if I want to refer an impedance across that due to the influence of Ohm's law, ZL prime is going to be equal to ZL times NP over NS squared, right? I've got that written down here. So these are the two rules that you have to apply to anything on the secondary side to move it over to the primary side.